A very warm welcome and good morning to one and all present here. I, Ananya, feel immensely pleasure to welcome our respected teachers, our esteemed guest speaker, Dr. Abhas Kumar Mitra, sir, and all the students on behalf of Lumen, the Physics and Electronics Society, Hansraj College, to one of the most awaited events for this academic session, Unveiling the Enigma of Black Holes. Lumen is a society where we aim at bringing the students of physics and electronics together and forming a close knit community which provides a platform where each individual gets to learn, grow, and share knowledge and ideas. We constantly work on providing varied learning opportunities to our fellow students through events and activities like knowledgeable workshops, insightful webinars, and competitions, all aimed at grooming students, enhancing their knowledge base, and furnishing desired skills. Today's session, Unveiling the Enigma of Black Holes, is the highly awaited session on the intriguing and fascinating subject of black holes, where our esteemed speaker would give insights on his book, The Rise and Fall of the Black Hole Paradigm. We hope that this session satiates our quest for knowledge and opens our minds for scientific ideas to usher in. For today's session, we have with us our highly esteemed speaker, Dr. Abhas Kumar Mitra sir, an astrophysicist who is known worldwide for his distinct take on understanding of black holes, dark energy, and Big Bang theory, and is accredited of resolving the black hole information paradox much earlier and in a more superior way than Stephen Hawking. Abhas sir is currently adjunct professor at Homi Bhabha National Institute. He is the member of the International Astronomical Union and a former full member of the American Astronomical Society. He headed the theoretical astrophysics section of the Bhabha Atomic Research Center, Mumbai from 2005 to 2015. In 1989, he won the first prize at the Young Physicists Colloquium organized by the Indian Physical Society. He has authored mostly single-handedly more than 100 research papers and articles on a wide array of topics ranging from high-energy astrophysics to general relativity and cosmology. He is the author of the book, The Rise and Fall of the Black Hole Paradigm, which appears as one of the bestsellers in astrophysics and astronomy. He has delivered 9 TED Talks and has been invited as chief guest or speaker to numerous events at various prestigious educational institutions across the country. We are honored to have you with us, sir. With this, I request you to please begin with the session. Thank you, and over to you, sir.
Hello. Good morning.
Yes, sir, you are audible. Good morning, sir.
So, thank you very much, Ananya, for the kind introduction. And I am thankful to Lumen, the Society for Physics and Electronics of Hansraj College, Delhi. And in particular, I am thankful to Jisant for inviting me. And I have told that, Ananya, I am thankful for your kind introduction.
Thank you, sir.
Now, normally I give talks, you refer to many talks, often they are superficial because I avoid technicalities. But you seem to be a little extra serious, sincere. So I would take the liberty of being little technical. Few slides would be slightly technical, and kindly bear with me, because you genuinely want to unveil, the enigma and black holes. So for that, I will have to go, I have to dig a little deeper. So excuse me, and during the question session, you can ask me any questions, and I would be very glad to answer all kinds of questions without hesitation. Kindly ask me all kinds of questions. Yeah, so, and that would be most welcome. As long as you wish, I am ready for answering. Now I should start my presentation, okay, without much ado. So I am starting my share slides. So first thing, I have already introduced that it is a talk on my book, Rise and Fall of the Black Hole Paradigm, which was published by Pan Macmillan this year only at the And it dwells indeed on the history of black holes, enigmas of black holes, and more importantly, their resolution. They say there is no resolution, but there are resolutions. And at the very beginning, I will start with the history of black holes. In Newtonian physics, the concept of black hole came more than 200 years ago, but I won't go into it. I will go into relativity only. So by the end of 1915, general theory of relativity got finalized by Albert Einstein and also David Hilbert. Although formally it called that gravity is property of space-time, in fact curvature of space-time, and there are tensorial equations, actual solution is extremely difficult, not only then, even now, very few solutions are there except after more than 100 years. So mathematicians wanted to solve the simplest physical problem, a single point mass in the universe and nothing else. And that point mass, whenever we say point mass is a finite mass, so it becomes density is infinite. If really a point would be there, so it means we begin with a singularity. So the black hole solution, say single point mass, and then it dwelt on this thing, the surrounding space-time around it, vacuum space-time. And it used in general relativity, coordinates are very important. You can go to various coordinates, not only x, y, and spherical coordinates, cylindrical, but much more convoluted coordinates. But the coordinate which you use for spherical space-time is big R. And what is bigger? Area of a sphere is 4 pi r square, surface area, and that remains valid in general relativity also. The 4 pi r square, so R is physically significant coordinate. And if I keep a source here at the origin, then the intensity falls off as 1 over r square. So this is a luminosity distance also. Now again, let me summarize. So spherically symmetric black hole is just a point mass M and the surrounding vacuum. Vacuum up to a certain radius to gm over c square. This gm over c square is called Schwarzschild radius in the name of Carl Schwarzschild. And this physically what it means that this is a very small radius. So sun has a mass of around 10 raised to the power 30 kg, which means trillion millions kg. And it has radius of around 7 lakh kilometers. So it is quite diffuse. But Schwarzschild radius here is only 3 kilometers, which means that if sun would contract up to 3 kilometers without losing any mass energy, retaining the mass, then it would come to its Schwarzschild radius, and so it is called Schwarzschild surface, and it would finally converge to a mass point. It would become a black hole. So this is the idea. And within this surface, nothing can stay put. Sometimes there's even space cannot stay put. So if a light is directed outward, even then light rays would fall inward. So this is perplexing, nobody understands, but mathematically everything is possible. This is the concept of black holes. That this is called trapped region. Within the black hole, there is a trapped region, and the event horizon is the boundary. Red line is the boundary. And beyond it, light can escape, anything can escape, but within it, nothing can escape. Everything must fall down. So this is the strange thing. And at the very beginning, I tell you, the solution came. Einstein was not happy. He told that black holes cannot be real thing. Now I will explain why he said so. And for that, but yet black holes are very important in astrophysics and physics. Why? For that, we need to know the compact stars. In real world cosmos, there are many astrophysical phenomena, and we have detected many compact objects, which have very deep potential well. What is potential well? Even in Newtonian gravity, it is Gm over R. So if it is smaller and smaller, then the well is stronger and deeper. So what happens when it is deeper? Then particles falling on it may acquire even the speed of light. Then they may collide and they can generate high energy processes. So that is this thing is important, Gm over R. But in physics, often we go for dimensionless quantities. That becomes easier for description. We make it dimensionless, Gm over R. We divide it by c square. C is the speed of light, which is very large, very large in the vacuum. So it becomes a very small number. So for sun, which is so massive and 7 lakh kilometer radius. So this becomes only 3 parts in a million. So relativistically, Sun is not compact at all. Its compactness is of the order of only 1 millionth, few millions. So it is diffuse. We cannot expect much high energy physics around Sun. Next come white dwarfs. They could be 100 times more compact. The radius could be like that of Earth. There could be a bigger white dwarf also, less compact. But if it is so, it could be 100 times compact. So its compactness could be, say, 3 parts in 1,000. So which is relativistically reasonably good. But real compactness comes for neutron star, you have heard. So neutron star also can have a mass of solar mass, but its radius is only 10 kilometer. That means its gravitational potential extremely well. So 10 kilometers is the, and Delhi has a radius of around 50 kilometers these days. So it is only 10 kilometers. And here, lot of astrophysical things happen important because particles matter, it attracts matter with very high speed, almost 10% of light, speed of light. And more importantly, it has strong magnetic field. Whenever a star contracts, the magnetic field increases. Sun has magnetic field around 1 Gauss. So within a refrigerator, magnetic field around 20 Gauss. White dwarfs are much more compact. So they have more magnetic field, could be thousands of Gauss. And neutron stars have mind-boggling magnetic field. It could be 1 trillion Gauss. 1 trillion means 10,000 in our Indian language, 10,000 crores Gauss. And they are so neutron stars very important for astrophysics. And so as I told, within the galaxy, there is a mass limit. White dwarfs cannot be more massive than 1.5 solar mass. Neutron star, though very important, can be only 3 solar mass, not more than that. But it is believed that black holes could be of infinite mass because they are just a point. You can mathematically imagine infinite mass. And some of the compact objects within our galaxy have masses of 10 solar mass or even 20 solar mass. So they cannot be neutron star. So then it is very natural to think that they are black holes. And even before that, if we go away from our galaxy, there are some galaxies which emit a lot of radiation, radio, star, not only optical, radio, then X-rays. They are called active galaxies and quasars. So their compactness, compact object is there, and they could be millions or billions of solar masses. Certainly they cannot be neutron star. What? So it was very natural to think that they are only black holes, because after all, black holes theories were there. And when we talk about neutron stars and why black holes are important, again, I would go dig a little deeper. So why black holes are infinitely compact? So suppose somebody is climbing a very high flight of stairs, then he or she would get tired. Why? Because when he's working against gravity, and then you lose energy. Similar thing happens when light leaves a compact object or anything, sun. So here energy is more, but as it leaves, its energy E decreases. E decreases means frequency decreases and wavelength increases. When wavelength increases, red has more wavelength than blue. So this process is called reddening. So if light leaves sun, actually whatever we get, whatever change by 1 millionth, we get more wavelength from sun. From neutron star, we get around 1.1 times more, whatever the light of wavelength is there on the surface of the neutron star. And this redshift is measured by this thing. Say I said that this Schwarzschild radius is there to Gm over c square. Here I have suppressed G and C. They are there in the background. And then Schwarzschild radius divided by R, the radius. And this quantity will be always very important. Bear in mind 1 minus 2m over R. So this gives the real general relativistic measure of the potential. Now you see for an event horizon, which is earlier called Schwarzschild radius, R is equal to 2m. Then 2m over R is unity. Then this factor 1 minus 2m over R is 0. and its inverse is infinite. So that means for a neutron star, 1 plus z or 1 plus z is infinite. So that means neutron star actual compactness is infinite. So black hole actual compactness is infinite. So if light leaves a black hole, if you can imagine, then it will have zero energy. When it would go far away, it will not have any energy. That is also one of the reasons physically we cannot see black holes. Nothing, nobody can observe strict black hole or event horizon. Again, I'll dig a little deeper. So we talk of gravity. So what is meant by gravity? So Newtonian gravitation also, two particles attract one another with the gravitational force G, big M, small m over r square. And for a unit mass particle, we get acceleration due to gravity G m over r square, which is around 981 CGS unit on the surface of the Earth. It would be different on different stars and planets. Now, this is a measure of gravity. But in general relativity, what happens, I would come later again, this increases. This increases by a factor of 1 plus z. So normally for neutron star, again, this means acceleration will change by a small factor 1.1. But for black hole, it will change for infinite factor. There is another measure. We know tides happen. Tides happen because moon pulls the water of the seas or oceans. But why tides happen? Because gravitational attraction is different from on the two sides of the Earth. So there is a differential acceleration that causes tides. So tidal acceleration is differential. So when you differentiate r square, you get r cube. So essentially tidal acceleration is gm over r cube. Now general relativity, I told that gravity is curvature of space-time. It is a technical thing, let's not bother much about it. But what is reassuring is that this boils down, the space-time curvature boils down to tidal acceleration. For a spherical star, this is called Kreisman scalar. I won't go into it. This space-time curvature, again, I have dropped some c square or other factors. It is gm over r cube. So this is the almost like Newtonian case, eventual space-time curvature. That means if the r is large, like surface of Earth, curvature is small. If r is small, then like a football, curvature is large. And now I beg your pardon for few words about special and general relativity. Now in Newtonian physics, you know, this interval of distance is constant. Means one bird is flying, suppose 6 inches its length. Someone measures from sitting in a ground. So somebody moving in a train will also measure the same thing. Somebody moving in a rocket will also measure the length of the bird as 6 centimeters, 6 inches. Similarly, some incidents happen, suppose cracker burst, 1 second duration. So Newtonian gravity, somebody sitting at the bottom of a mountain will measure it 1 second. Somebody on the top of peak of the mountain will also measure it 1 second. And somebody moving with a high-speed rocket will also measure it 1 second. So dx or dt are same for all, and that is called invariant. They are invariant. Now we come to special relativity. Special relativity changes. So if the length of the bird is 6 inches, somebody moving in a rocket would measure it slightly different. And somebody moving close to the speed of light will see much more difference. Similarly, the cracker duration is 1 second in the room. Somebody moving in a rocket would measure a different interval. So this is there flexible. Neither dx nor dt are same. They are not invariant. In contrast, what is invariant is c square dt square, which is a dimension of distance, minus dx square. So space and time get intermingled, and this is called space-time interval. This remains same to all the observers. So this is the crux of the special theory of relativity from a mathematical point of view. Suppose we apply this to a particle moving with a speed v is equal to dx dt. So v is equal to dx dt, we can express the space-time interval as this way: dt square into c square minus v square. And the special relativity says the space-time interval is always positive, greater than 0 for a particle with a finite mass. What it means then? That means v is always less than c. You have heard special relativity, all particles with finite masses move with a speed less than speed of light in vacuum. So this is the always positive. Bear in mind, space-time interval is always positive for real particles with mass or matter with mass. On the other hand, photons, the corpuscles of light, they always move by definition with the speed of c. Special postulate of special relativity, v is equal to c, space-time interval is 0. So for space-time interval is 0 for massless particles or photons. Special relativity, not only special, we'll go to general relativity also. There also, general relativity also, lights always move with space-time interval 0. And note another thing, the space-time interval has two. One part is positive, one is negative. So we call this signature, plus and minus 1. This is the signature. The signature of space-time is plus and minus 1. Now, what is when you go to general relativity, space and time interval change not only with relative motion, but also with locations. So one observer is sitting on the ground and measuring the length of a bird is 6 inches. Somebody sitting on top of the mountain will measure a different length. Somebody measuring a cracker, a duration 1 second, and somebody on the peak of the mountain will measure it slightly different. So, and there is no relative motion. So even if there is relative motion, because of different gravity, space and time intervals change. Of course, with the motion also they will change. So now space-time interval again, but this space-time interval again is positive for real particles with masses. But for photons, again it is 0. Now special theory relativity, one dimension space-time interval, I have dropped c here. So dt square minus in one dimension minus dr square. No gravity, special relativity, but now we have gravity. So around a spherical object vacuum, new factor comes because of gravity, 1 minus 2m over r. On the time part, and on the special part, 1 minus 2m over r inverse of it. So what does it mean? And these causes havoc. So when you go to r is equal to 2m, this interval becomes, this is 0. 1 minus 2m r becomes 0. See, 2m over r becomes 1, and this factor 1 minus 2m over 0. So this interval becomes now 0. So time component, the coefficient becomes now 0. And on the space component is the inverse of it, it becomes infinite. So this is called, there is a singularity in the space-time interval. And this is one of the major reasons Einstein and most of the founding fathers and peculiar properties of black hole. They said mathematically solution is fine, but in real life we cannot have a black hole. A star cannot contract up to 2m Schwarzschild radius. And even more perplexing enigma, if you go inside, now r is greater than 2m, then this factor becomes negative. If this becomes negative, this plus becomes negative. So time interval was positive, now it becomes negative. And on the other hand, spatial part was negative. Now because this becomes negative, this becomes positive. So if black hole would exist, finite mass, within it, time part changes from plus to minus, and spatial part changes from minus to plus. So as if space and time swap their roles. So mathematically this is fine, but physically even now we cannot conceive it, and there are a lot of inconsistencies. But despite that thing, people believe in black holes. 99% of mainstream physicists believe in black holes. And they defend it. And because of there are many reasons, they told that oddities at r is equal to 2m, something going to 0, something becoming infinity, these properties can be removed by re-expressing the solution. Say coordinate we used is r, the luminosity distance, and some time. They can be changed in principle. And this process started say 1922 and 1960s. So final form of black hole, space-time, whatever there. And they said everything is fine. We can go inside the black hole, outside on the surface. There is no problem. With new coordinates, we can set everything right. This is one of the major reasons. All teachers will say this thing when you go to university and learn black hole. Even in Princeton, they would say this thing. Then there is another thing, space-time curvature. I said space-time curvature essentially m over RQ. Now on the surface of the black hole is 2m, R is 2m. Then this becomes essentially m over m cube. So that means 1 over m square. And this looks on the so finite, but there is a catch here. This is finite only when you assume that mass of the black hole is finite. If it is 0, again, this should become infinite. And then another thing is that they emphasize that black hole is just a coordinate singularity. It is, you chose the wrong coordinate, so you are getting some peculiar things. And it is nothing physically, it has no importance. So an observer falling inside a black hole would notice nothing. Nothing special happens there. It's a perfectly normal surface. And on the top of it, in 1939, for the first time, gravitational collapse, a star is collapsing. This equation in general relativity scholars, it is solved by Oppenheimer and Snyder. And they showed that a uniform density massive star, it should collapse to become a black hole. Again, there are a lot of catch here. So and once this thing was there, they told, okay, now stars collapse black holes and everything is fine. So all these compact objects must be black holes. And then from 1950s, we actually went on discovering compact objects. And they cannot be white dwarfs, they cannot be neutron stars, so they must be black holes. Now I'll attack all these defenses. One of the defense was that you can go to a new coordinate system and remove all the peculiarities. Now say there is a beautiful rose. I can trace it one-to-one on a graph paper. When I do this, I get a real picture of the rose. Or when you take photograph, we do one-to-one photographing. Our image gives the real picture. But suppose I have some other distorted software. On a graph paper, I change to semi-log. If I do say x-axis semi-log, y-axis unchanged, then my picture would change, can completely change completely. Then it would link, it would appear that as if it is shrunk to a line. Mathematically, this can be done. But does it mean the physical reality has changed? Just because you are free to use any coordinate, we do not have the liberty to change the physical reality. So mathematically, you can do any kind of mathematics that does not change the physical reality. And moreover, all these changes, new coordinates, they involve the parameter log of 1 minus 2m over r. Now what happens, this is a little bit of mathematics, actually school level mathematics. At r is equal to 2m, this factor becomes 1 and this log, it becomes log of 0. Log of 0, if you recall, it's minus infinity, it is infinity. So in transformations, mathematical transformation, you are not allowed to use something infinite. So as if one infinity is hiding another infinity. This happens, this is how you hide the peculiarities on the event horizon by mathematical transformations. Now I'll come to another defense of black holes. So they tell that even now all the professors, even in Princeton, Cambridge, Oxford, they will say, oh, nothing happens on the event horizon, a particle can fall freely, observer would see nothing. This is wrong. And this wrong was pointed out only rather recently, 1982. A small paper came in General Relativity Gravitation. It showed that even a free-falling observer can detect the event horizon. What happens, he can measure a physically measurable quantity. They define a quantity, it changes sign. It is negative outside the black hole, inside it is positive, and on the surface it is 0. So an observer can very well measure that it is changing sign, he can detect the black hole. And this is, I have talked of spherical black hole, it is spinning black hole, charged black hole, everywhere this is there. So all event horizons can be detected. which means it is indeed a very special surface, which when black hole paradigm was established in 1960, nobody knew. This paper came in 1982, but already black hole become biggest paradigm in physics. So people chose to ignore this thing, or they said they will ignore, or sometimes they refer, but still they will not defend this point. Then now it is a very special surface, your defense is gone. So now I am telling, because of this thing, actually black hole paradigm almost fell in 1982, much before I wrote my book. And another thing, now they also say acceleration horizon is a very special, no special surface, and nothing happens there. But 1981, a small paper came in American Journal of Physics, and it actually showed what I have been telling, that acceleration due to gravity one can measure sitting outside the event horizon. So it has a form gm over r square kind of thing in Newtonian, but here it increases by a factor 1 plus z. And as if one approaches the event horizon, since z becomes infinite, it becomes infinite. So if one measures measured quantity tend to infinite. So this is the most physical reasonable thing, strength of gravity. It has become infinite right on the event horizon. It is measurable. So that means event horizon not only a special surface, it is actually a singular surface. So all the singularities in the coming in the space-time, 1 plus the special part going to infinity. So that is because of the same thing, 1 minus that z part is going to infinity. So you cannot change this by coordinates, even you can hide it. And then redshift is infinite. Forget this thing. Redshift is measurable. So redshift infinite by definition in a black hole means it is a very special surface. It is measuring effect. The very fact that we cannot view a black hole because redshift is infinite. So that means it is a very special surface. Forget your mathematics that you can do some tricks there and hide locally. But redshift remains redshift. So and then it has a converse thing. Suppose I am dropping a particle from far away to if a black hole would be there. On the event horizon, locally measured energy becomes infinite. So energy cannot be infinite anywhere. And energy is infinite. There is a lot of particle can decay, a lot of things should be observable. So these are all physical effects, even without these two things. So it is a special subject, and there are singular effects. For these reasons, black holes should not exist. And whatever Einstein and others told, founding fathers, stars cannot contract up to black hole for some reason or another, which they could not point out, which I started pointing out in 2000, since 2000. Now, the gravitational pull-ups. I told there is a solution in gravitational pull-ups, which apparently shows black hole can be found. Let me review it. That there is no exact solution for black hole formation for realistic gravitational pull-ups. What is realistic gravitational pull-ups? There is always emission of radiation. Whenever a star contracts, it emits radiation, it becomes hotter. And there is involved, what are the things? The things involved as star, all real things have viscosity. There is transport of heat and radiation. These things cannot be incorporated in mathematical equation and nothing can be solved. So then how can one solve? One can solve by setting everything zero, ignoring everything. So what Oppenheimer and Snyder did, they not only assume the star to uniform density, there is no pressure. Now in real life, everything has pressure. See these houses there. These houses there is pressure. In the cement or concrete, there are chemical bondings. There existing pressure against gravity. So in water, wood is floating because there is force, resistance, pressure, force. And if you assume that the water has no pressure, then immediately the wood would sink. But it does not sink because pressure is there. By mathematics, you cannot say that water has no pressure. You can do mathematics, but it is physically meaningless. And when it is losing energy, stars always lose mass also because energy is mc square. E is mc square energy, star loses energy. E is equal to mc square becomes lower and lower. So they are always losing mass. What happens? Mass can not only reduced, it can go to zero in general relativity. So mass is total energy. Rest mass, positive mass, heat positive, internal energy, same anything, magnetic energy or anything positive. But gravitational energy is negative. In Newtonian case, it is minus gm square over r. As gravity progresses, this becomes the dominating things as r shrinks and shrinks. So they can together balance each other, and in principle, total mass energy can go to zero during relativistic collapse. So mass energy zero means mass can go to zero. So whatever the Oppenheimer-Snyder paper is not physically correct. And this I have shown repeatedly. In fact, I wrote two papers, one in 2011, the fallacy of Oppenheimer-Snyder collapse. There is no relativistic collapse. It is all mathematical illusion by taking pressure is equal to zero. Then again in 2013, I wrote another paper in International Journal of Modern Physics T. The pressure is equal to zero only when density is zero, mathematics. So it means nothing. If density is zero, then mass is zero. So whatever I am telling, then mass can go to zero. So you assume that mass is remain unchanged, density finite, then you are giving a mathematical illusion. So it is no example for black hole formation. Now, what other things I showed? Suppose a test particle is there and you assume a black hole is there. It is approaching a black hole surface, the event horizon. Then what I showed, this is in my paper starting from 1998. The space-time interval associated with the motion of the test particle, it depends on the sign of that important factor 1 minus 2m over r. And this always has to be positive as per special and general theory of relativity if it is a finite mass. But what happens if the particle would reach the event horizon r is equal to 2m, then this becomes zero. The sign becomes positive, it was zero, and if it would go inside, it would be negative, and this is not allowed. So that is the reason I told, and one can verify this thing. Actually, this derivation is relatively easy, that there should not be any black hole, and if at all, there should not be any interior. So mathematically, black hole mass should be zero. So even if your equations are correct, but actually mathematically mass is zero, this is illusion. Also, if one finds out this trajectory, so only when m is equal to zero, test particle can never reach. So it is called proper time would be infinite, it would never reach. So from every perspective, mathematically black hole is, if it is correct, but it is mass is zero, so it is an illusion. So all the finite mass objects, they are not exact black holes. They are black holes who are black hole mimicker. They look like black hole, they are very compact, but they do not have horizon. These I have been shouting from 1998, and earlier people have told, but they could not show why it is so. Then what more I showed, then I was struggling, if a star is collapsing, what should be the sign of the space-time curvature? These I started doing in 1998, and there were many errors even in my confusions. But this thing I removed later in 2004, and correctly showed that again the signature of the space-time interval for matter falling again is same, 1 minus 2m over r. So that means if r is equal to 2m, this is called if horizon kind of thing is formed, this sign would become zero, which is not allowed. And inside it again it becomes negative, this is not allowed. That means we'll never attain a r is equal to 2m surface. So interior of the black hole is r is less than 2m, that is called trapped region. That is never formed. So we have heard the name of Rosa Penrose, who got Nobel Prize last year. So in 1964, Penrose started working on gravitation. So he got moved by this Oppenheimer-Snyder solution, and he assumed that the stars collapse. Sometimes they would be like, their interior would be like interior of black holes. Technically, they would become trapped region. And I showed this assumption is wrong. They would never become trapped region. So black hole is never formed. And this, in a journal, it is very difficult to publish these papers when you contradict Penrose. It was published in Indian Journal 2019 with a lot of difficulty. Then what else I showed? If they are not black holes, what are they? So what I pointed out that the physical thing, no, so theoretical physics, quantum gravity, hanky-panky,